Looks like we're just about there. Welcome back, everyone, so far. Well, looks like we can begin. Welcome back, folks. We're now into the third week, so just 13 more to go after this one. For today's class, we're going to finish off section 2.3. We pretty much had it finished, but I didn't want to rush through the last example on Wednesday's class. So we'll finish off this one and then move into section 2.4. But any questions or comments, folks, before we get started with today's work? Okay, well, with what we're at so far, after we finish off section 2.3 and section 2.4, only remaining section in chapter 2 that we're going to work on is the section on functions. Then we're going to move over to chapter 3, working on logic, which is a pretty exciting unit. As far as the first exam goes, by the end of this third week, I'm going to be finalizing the information that should go here, the definite coverage, as well as the review problems. So that's where we're at so far. That's where we're going. It looks like exam 1 is going to be majorly over chapter 2, maybe a couple sections in the next chapter 3. That's a pretty short set of announcements compared to the first day. Any questions at all then, folks, before we begin in our section 2.3? Okay, let's get started. So again, we didn't leave off too much, but this is not a topic you want to rush in about 4 or 5 minutes. So now coming back to it, we can give this a lot better attention and detail. So we're referring to in definition 2.33, the power set. Anytime we're trying to indicate a power set, we always write it out this way with a script P in front to indicate the power set. It takes a set itself, a set S, so the set S goes inside there. And all the power set does is it's the set of every single subset of S itself. So that means it would contain the empty set. The empty set is a subset of S. It would contain S itself because we're talking about subset equal. And while it's true, S is not a proper subset of itself. So we write that slash symbol here to say not a proper subset. It's also true that S is subset equal to itself. That little bar down below, just like less than or equals, is saying we're including the possibility that S equals itself. So we have the set of all subsets of S going inside the power set. That means, again, the empty set, the set S itself is contained there, and every other subset A as well. Sometimes this can be kind of difficult to compute, especially when we don't know how many actual sets is a subset of the original set S. Sometimes there could be lots of sets. Sets that we won't work on directly in this class, for example, are sets like this one. The closed interval from 0 to 1 has a mind-boggling number of subsets that you could discuss on this. So that discussion can get way out of hand pretty quickly. But the good thing about the power set here is, again, there's a definite way to compute it and a definite way to know if you have the right number of elements inside your power set. It goes pretty much like this. If we write out the cardinality of the power set of S, let me try to fix my parenthesis first. And I think I need more space for that. Let me just try that all out once more. If we want to know the size of the set P of S, let me try one more time writing out the power set. You don't have to put down a fancy P, but it's good to try to do a little bit of cursive just to indicate it's a special kind of operation we're doing here. So the size of the power set of S is equal to 2 to the power of the size of S. Our author mentions in the reading, this is the reason it's referred to as the power set, because of this operation right here. But this only qualifies as long as S is a finite set. So we'll use this operation right here, this formula here, to let us know if we have the right amount of elements when we go to find the power set in this example. Any questions first, folks, before we give it a try? Okay, so our goal is to find every possible subset of this set A right here. Let's highlight that in blue. Well, maybe let's leave it just as it is. First thing we'll do is look at the size of the set A. There's 4 elements inside that set, so we'll say size of A is 4. Because we're computing the power set, we also want to know what is the size of the power set of A. This will be 2 to the size of A, which means it's 2 to the power 4. So altogether, we're expecting 16 elements inside the power set of A. So let's start writing it out. Power set of A equals, it's a set of all the subsets. So first one we ought to throw in there is the good old empty set. That belongs. So this is going as small as possible. And kind of my strategy for making sure I've got all 16 elements inside the power set is to build up from here. So I put in the smallest possible set we could write down, the set with nothing, the empty set. Now coming back up here in the major set A, I would probably want to next write down all the singleton sets. These are the sets that contain exactly one element. So that'd be the set containing only 0, set containing only 1, the set containing only X, and finally, the set that contains just Y. So that's our first bit batched down. We have 1, 5, so 9 more to go. But then we can build from this even further. Let's go to all the subsets that have exactly 2 elements. Here we want to be really methodical so we don't miss anything. So I'm going to start with 0. I'll include the next element, 1. For the next one, let's also include 0. And then the next element, X. So this is just my way of trying to form all sets of exactly 2 elements. Next element is going to be 0, and then Y. So let's keep on going. If I want to form the other pairwise 2 set element, let me get that back here. To get all the rest of the 2 set elements, sets of subsets from here, next thing we want to do is just lose 0 and move over to 1. So that'll be the set that contains 1. We can take the element right to the right of the red dot and throw in X. Then 1 and Y. Now that takes care of all the sets of exactly 2 elements that involve 1. It involves 0, 1 from here, 1X, 1Y. Continuing with that strategy, we move over to X. But the only set of 2 elements I could form here would just be X and Y. Because the order doesn't matter in all these sets, this is every single subset containing exactly 2 elements coming from A. But again, we need 16 sets altogether. Let's count them. We had 5, 6, 7, 8, 9, 10, 11. So we have 5 more sets to go. That's okay, we can definitely find them. But any questions so far to this stage, folks? Okay, we're definitely getting there. And you can imagine how tedious this would have been if A had 5 elements. Then the power set, the set of every single subset of A, would contain 32 elements, and that would actually just take too long to write down. I can never make that a real exam question. I would say size 4 is about as high as I could go to make this a reasonable by hand problem. But let's keep on going. We got the empty set, the singleton sets, the sets of cardinality 2. Now comes in the sets with exactly 3 elements. As before, just imagine you're leaving one element off. Let's start with 0. If we leave off 0, the set would contain 1, X, and Y. So that's 1 triple. Next element I want to leave off is the 1. So our set now has 0, X, and Y. Next, we're going to omit X. So that set is 0, 1, and Y. And finally, The set where we omit y would go 0, 1x. So one last set to throw inside here. It's the largest set of all, just the set A itself. And you could just write it out with curly braces, 0, 1, x, y. I think it's a good idea, actual good call to write it out this way, because then this is a reminder that the set A is always inside the power set, and so is the empty set. So I usually write out in this way, going small and then going large. But again, we're expecting 16 elements, so let's make really sure. Here's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and we found it. The 16th element is the set A itself. So that's the power set. Lots of different things you can do with this power set. It doesn't exist in isolation. It just kind of feels that way in section 2.3, where we have a lot of disconnected pieces of information about sets. If you're curious about what an application could be to this, I think we hinted at it before. In probability theory, we can define a probability function in this kind of way. It's a function confusingly defined by P, think probability of an event A, but its domain is the power set of A. There's different ways to define probability functions, but this is a specific one for finite events. It outputs a number between 0 and 1, including the boundaries. And we'll later on, once we get to the section on functions, call this the domain. This is the codomain. And P is the probability set function. And this is one of the reasons why probability, even though it's something that you probably have done a lot in different math classes, it's a hard class to really do from bottom up. It's like a 300 level class in the math department. And that's because for one probability model, you're always using the power set for your most basic option, the probability function in the first place. And then if you're dealing with the normal distribution, you're doing something totally different than this even. It's a whole new probability model. But the major takeaway from this is if we have to write down the set of all sets, this is the process. This first line is optional, but it's always good to know if you have the right number of sets. And just like in the last problem, when you do the problem on writing down all partitions of a set, you could look up Bell's number and determine, do you really have the right number of partitions based on your size of the set? That was a pretty complicated formula, but the further and further we get into this book, the more attackable that formula actually becomes. It's a recursive formula on one hand, and then something you'd have to use in calculus 2 on the other hand. But we did it, folks. That's the conclusion of this section on sets. Any last questions or comments whatsoever before we go to section 2.4? Looks like it's next. Okay, let me get this saved up and we'll go over to that next section. Oh, didn't mean to do that. Let me fix the participant window. There we go. Okay, well, here's our next section, folks. The last section was all about unordered collections, so we're dealing with sets. Now we're completely turning this all around. We're still looking at sets, but now we're interested in sets that have a definite order attached to them. Those new kinds of sets will indicate by calling them a sequence. Will be an ordered now collection of objects. And a lot of examples would be, for example, an ordered pair. In the Cartesian coordinate system, you write down pairs x and y to refer to a first coordinate and a second coordinate. So just that alone, if you wrote it like this, that would be confusing. Your coordinates shouldn't have curly braces. That would assume order doesn't matter. But that's not the case. If we're plotting something, we either go like this, x, y, because now order is suddenly very fundamental to our set. So if order is important, we can call it a sequence, but for folks who have taken Calculus 2, we're only dealing with finite sequences in this course. In Calculus 2, they deal with the infinite sequences for the very, very curious. Our author doesn't even use that notation either, where the red dot is. Our author prefers to use this notation, bracket x comma y, end the bracket. This is pretty familiar if you've taken, say, Calculus 3, other physics courses, for putting together ordered collections. So that's going to be our new type of content here. And there's really a lot you can say once you get into sequences because, well, vectors aren't any different. If you wrote down, say, xy in this way, you're looking at a vector, say, in the Calculus 3 content. If you write down xy in this way, you're looking at a vector, but in more of a linear algebra type of context. Either way, you're just dealing with a sequence of finite length. Just for a couple of examples, I thought this one is interesting for just the context of this kind of course. A 5-tuple that makes internet work is this one right here. This is the Transmission Control Protocol TCP connection, where we have various IP addresses. I'm not too sure what these numbers would mean. Anyone who is more familiar with internet architecture, feel free to chime in. And then the last part of this 5-tuple is just saying the type of transmission protocol. So sequences are interesting, but I don't have any big examples here. These are just things we're very familiar with. What we're moving into really next, this is where the homework problems would start in the homework, is dealing with Cartesian products. So I guess this is where the section really gets started. But any questions at all, folks, with the earlier definition? Okay, so think of section 2.3 as a really wild landscape. It's very fundamental to mathematics. It turns out you can't even define function without defining set first. But 2.4 is trying to add order to what was happening in section 2.3. So everything in its position has a meaning. So next, dealing with a Cartesian product, what we do here is we start with two sets, A and B. The Cartesian product written down this way, A cross B, think of a cross product, is a collection that starts off this way. We take ordered pairs A to B. The elements A have only the requirement that they came from the larger set A. The elements B have the requirement that came from the other larger set B. So the moment we discuss two sets, they have to be non-empty sets. This would be their cross product. It's not strictly that they have to be non-empty, but if you write down something like an empty set, cross product any set whatsoever, you don't get anything whatsoever because the first condition will fail. Nothing comes out of the empty set. So this would just be the empty set itself. You know, that makes sense, right? That's why we kind of have a multiplication symbol here in a certain sense. In a way, it seems like we're saying 0 times something results in 0. Intuitively, that just seems like it would make sense based off this notation as well. So other Cartesian products you've definitely seen in your mathematical careers would be things like R2, R3, R4, and so on. It's just R cross R. Maybe not as exciting because that's the same set cross product with itself, but this is what the entries would look like in R2 or R cross R. This is just the ordinary Cartesian coordinate system. For people who are familiar with SQL programming language, Cartesian products is also used within that language. I'll leave the reading here up to you since a lot of people are not necessarily interested in specific programming language examples. But it's cool to know that this is implemented in a lot of different ways, just not as a mathematical curiosity. What we'll do in example 1 to match those homework problems is just practice taking cross products, Cartesian products rather. So any questions first, folks, before we give example 1 a try? Okay, so here's how this goes. Find the Cartesian product of the two given sets. So we have A is xy, B is 1, 2, 3. Thought that was a highlighter. Let me try again. One thing that we could add to this just to get us started on the right track, let's add a counting formula as well to go along with it. Sorry, I had my colors mixed up. Okay, so the formula goes like this. If the size of A and the size of B are finite, so not sets with infinite length, we have finite number of elements in both sets, then the size of A cross B equals the size of A. This is an ordinary multiplication. I'll just put the bullet there just for emphasis, times the size of B. And that's a great formula to have on its own, because again, whether you're doing a Cartesian product, a power set, or a partition of a set, it's just good to know how many elements are you expected to write down as a check in itself. So in our problem right here, we can say the size of A, Cartesian product with B, would then be the size of A times the size of B. So in our problem, looks like we'll have just a 2 by 3. That is a little bit trickier than I thought, writing that out with color coding. But we're expecting 6 elements in this Cartesian product here. So let's write it out. A cross B is going to be equal to, well, it's a set of all the possible ordered pairs where A is the first coordinate, B is the second coordinate. Again, that makes sense. We're looking at ordered collections now. So we'll start off this way. With the set A, the first decision we have to decide is which element are we going to use. But you want to be pretty methodical with this so you don't miss any elements. I'll start with X. Then go down the lines of the entries over here in B. Almost kind of like a distribution. I'm associating X with 1, X with 2, and then X with 3. So it'll go X1. Let me know if I miss any of these entries. X2. I need to find a shortcut for switching colors. I think that would speed it up a little bit. X3. And again, that's only half of them. We're expecting 6. So the strategy I take next is move down just to the second element in the set A. It's going to be pretty much the same thing that we wrote above. The only difference here is the first element is going to be Y. The second elements are just going to be the 1, 2, 3 we've already laid down. So I usually go in this kind of 2-row system just to make sure everything is exactly where I expect it. So Y goes here, here, and here. So we're taking the element of Y here, pairing it with all possible elements of B, which run as 1, 2, and 3. At this stage, the size of the set is 6. And as long as we really didn't duplicate everything and wrote down all possibilities, this is all we're meant to do for this kind of problem. Does that look right to folks so far for this first Cartesian product? Okay, looks like 1 down, 1 more to go. So there's really not too much variation on this, except one thing you can do is make this one of the sets more abstract than normal. So that's this example. Another thing you could do is just add more sets. But if you add more sets, it's the same kind of idea here. Just imagine a third comma and you say C is in whatever the set was. But let's work up to that by working out part B first. First thing we probably want to know is how many elements is in the Cartesian product between A and the power set of A. And this would be the counting formula. The size of A, Cartesian product, the power set of A. By the formula right up here, that should just be the size of A, multiplied by the size of the power set of A. But, oh, hang on, I've got a parenthesis issue. Let me fix that. There we go. But then on the next hand, from the last section notes, we have a formula for this location. It'll turn into the size of A times the size of the power set, as long as the set of question is finite, is 2 to the power of size of A. So we get from here, this expression. I think we're now ready to calculate all these. The size of the set A was just 2. So this turns into 2 times 2 to the power of 2. So this is 2 by 4, or 8 elements total is what we're looking for on this one. Maybe a new page might be wise on this. Let me move this down. Well, now that we have that down, again, this is optional, but it's a good internal check as we start to write this out. We can now come back over here and begin expressing everything. But really, another step we probably should take before we get too far is we should deal with the power set of A here and just write it out, or else writing down the Cartesian product between these two, which would be extremely vague. So let's start off with a good old review problem, our second time doing a power set. The power set of A would begin with the empty set, and go back over here. The singletons would be the set containing 1, the set containing 2. Recall when we wrote the size of A, or the size of the power set of A here and got 4. Let's actually track that yellow highlighting. And that there was 4 sets total inside the power set. Any volunteers for saying what the missing set is? Good call. It's the total set A itself. You can either write it in as 1, 2, or with the symbol A. That's going to be a total stylistic choice up to you. So that's a set we're cross-producting with the original set A above here. So let's write out A, Cartesian product with power set of A is going to be equal to the set of all ordered pairs, where the first entry in your ordered pair is just a number, but the second entry in your ordered pair is an entire set. So it feels a lot more abstract, but really the port to part B is just to practice with the power set just a little bit more. So let's start off by writing 1. Next, I'll pair it off with the first set in the power set and just move on down the line. So we're expecting 4 entries here. So 1 in the empty set. Next, it's going to be 1. I'll keep using 1 until we run down with all the entries in the power set of A, and then just redo the whole thing over with 2 as the first entry. So now it's going to be 1, and the set containing just 1. And notice those curly braces here are actually important, because the second set is a set of sets. What we're throwing in as the second coordinate when we do the Cartesian product is a literal set. So from here, this must be a set. So we can't write 1, 1. We have to write 1, comma, the set containing just 1. Tedious, I know, but we'll get through it. Let's go to the next one. Next, it's going to be 1, 2. I said that wrong. It's going to be 1 and the set containing just 2. Takes a lot of oxygen to say it the right way. And finally, last set before we go to the second entries with 2 in the first position is going to be 1 and the set A. So now down below, we'll do the same thing all over again. But all we're doing this time is putting in the entry 2 as the first entry in every single one of these. So let me write in the structure. Then we just fill it in. So I'll go, oh, I already made a mistake. Let me go over here. We're throwing in all the other ordered pairs. So 2, 2, 2, and 2 would go into those positions. Then we've paired up with all the elements in the power set. So it goes empty set, the singleton. But really what my eyes are doing is just copying what we wrote above. Set containing just 2, set containing A. And this kind of organization, whenever you're doing something tedious like we just did, enumerating the entire Cartesian product, it's a good idea to be methodical and organized just so we know nothing is missing. In fact, let's do one last check on this. The size, oh, we already did that. The size of A times the power set of A should be of size 8. And that's what we have, 8 elements altogether. So we did it, folks. That's the Cartesian product of A with the power set of itself. You can imagine if this was 3 elements right here with the size of A, this would get really out of hand pretty quickly. But any last questions, folks, to this stage or through this problem? Okay, I think this one gets a little bit beyond what you see in the homework, but these problems are always good whenever you can connect back what you were just working on and put it in the larger stage that we're working on here with the new definition. Last thing we'll do on this set or this problem is just try once more with 3 different sets, which makes sense because, for example, R3, that's just R cross R cross R, and this refers to just ordinary 3-dimensional space. So a cross product with 3 different sets certainly is something that we ought to take a look at. These are things we've worked on, but this is just a more simplistic case where the sets are all finite. So color coding might not be the best here. There's a lot going on. Let's just write it in as A cross B cross C, but maybe first on the margin, A cross B cross C. So we're now doing a Cartesian product with 3 different sets. Anyone see what the size of this set ought to be? Good call, absolutely. The size of this is 8 because it's just the size of each one of these all multiplied together using the formula we saw above. Each set had size 2, 2, and 2. So just 2 by 2 by 2 gives us the size here. So we're expecting 8 entries altogether. Let's write them out carefully. I'm going to start by first taking A, leaving it fixed like this, coming over here on 4. I'm going to leave the 4 fixed as well. And what I'm changing is the 3 and the 5. So that's what my first 2 set or entries would look like. So 3 here, A, 4, and 5. And that looks like the number 9. Let me fix that one. So next thing to do is, after we fixed this entry, I want to fix this one right here. So we're pretty much just redoing these, but the entry in the middle is going to change to a 7. So let's write it out. We'll have a 7 come over here. We'll take the 3 first and then the 5. Next is A, 7, and 5. So that's half the list. We have 8 of them down. Dropping this down again. Here's what we'll do on the next one. Let's fix B and fix 4. Use up the entries 3, 5. Then we'll vary 4 so that 7 is fixed. Then use up the entries 3 and 5 again. You don't have to do it this way because this is overall right here a set. You can drop in these things in any order you want. These things do have a definite order though. We can't necessarily change these around unless it's part of the product. But doing it in this really slow methodical way, that's just a way to make sure we have everything. So let's go B, 4. First entry is going to be 3. Next it'll be B, 4, 5. Then we go over here. We're going to repeat that operation, but make our second entry a 7. Or you can notice, if you're looking at the list we're building out, they're pretty much duplicating except the first entry has changed to a B. So let's keep on that strategy. This one should be a B, 7, a 3. And the last one should be B, 7, and 5. At this stage, we have 8 entries. None of them are duplicates whatsoever. And so it looks like we really match the 8 elements we're expecting in this Cartesian product. That's one way to do it, but I like to do this as methodically and organized as possible because, again, I have a habit of just missing something off when I'm copying down a bunch of information. But any questions at all, folks, on dealing with that product? Okay, pretty riveting stuff. Next thing we're going to take a look at beyond that is dealing with a vector. But in a certain sense, we're kind of already looking at that. When we wrote down A43, we can think of that as a vector inside R3. But to be more formally, here's how the author would define vectors. It's a sequence in Rn. Again, that always feels weird. If you have taken Calculus 2, we mean specifically a finite sequence. The symbol Rn now says the Cartesian product with a real number line, n times with itself. N is going to be a positive integer. And for vector x in Rn, xi is just going to refer to the ith component of that vector x. So in physics, this is a structure that they study very, very deeply. The 0th component on this one is the time component, where c is the speed of light in the vacuum. And this portion is just R3 right here, ordinary space. So space-time in R4, the way the physicists study this thing, it's a pretty bizarro mathematical space, but you could think of it as this. R, that's the temporal dimension, cross R3. Those are the spatial dimensions, or just wrap it all together in R4 and indicate your vectors this way. So vectors are used all over the place. And this is an opportunity for us to look a little bit into vectors, some matrices next, and a bit of arithmetic with them. But we won't be going too far. We're just looking at some of the elements that might become useful later on in the book and some related examples. So again, if you take in linear algebra, this might look like a weird way to write down the vector, but think of that vector where the red dot is as being synonymous with x0, x1, x2, x3. And this is just a linear algebra way of saying the same kind of information. Other things we can say about our vectors is we're interested in the length of the vector. Sometimes we say instead of length, that symbol is referred to as the norm. To normalize a vector is to find its length and force the length of it to be 1. It's written out in this way. It's the summation of each entry, each component of the vector to the power of 2. And it's a unit vector if that length ever happens to be 1. Then down below, we have some interesting operations. The sum of vectors is written in this way, x plus y. But all we do is, for every index I, add together the ith component of both vector x and vector y at the same time. And that's the ith component of the new vector zi. So that's our sum. Sometimes we call this right here vector addition. And as opposed to addition, we have a couple ways to multiply vectors. The scalar product, or scalar multiplication. Is not really taking a vector times a vector. What we do instead is we grab a vector, a scalar that comes out of, A in R, a vector Z in Rn, and, let me back off. We take a vector X in Rn, scalar A in R, then the new vector Z that we produce still lives in Rn. And this is just a way to say, in essence, we go for every index, every component from the original vector X and multiply it by A. So that's a result of the scalar multiplication. Other products we have are the dot products, the cross products, which say something about the geometry of these vectors. And let's give this a try next on example 2. We'll see how the dot product goes on our upcoming examples. But any questions so far, folks, with that quick rundown of dealing with vectors? Okay, well, here's a smattering of vectors. They came from R2. First thing we're going to evaluate, just for the practice, is the length of the vector B given. So we want to take the length, or you could say the norm, of the vector -3, -5. There's a lot of ways to say what the formula should be for this. You can involve it with dot products, for example. But if we just use this structure up above, here's what it's saying. You're taking the square root of the sum of all the components squared. There's only 2 of them, so we don't need summation notation for our problem. We just needed it to write down the formula. We would be taking this component, squaring it, add this component squared, So we've got the square root of 9 plus 25 for the square root of 34. That doesn't reduce, so we'll leave it just as is. And this again tells us the distance that the vector -3 to -5 is away from the origin. So a really quick view of what we just computed is our vector -3, -5 is right here. So there's our vector B. We draw a directed segment from there to the origin. This refers to the length of B now. Let me try to say this is B. That's the length of B. And we computed this length from here to here to be just the square root of 34. Next, it looks like we have just a random arbitrary linear combination, mainly to work on dealing with the vector addition. And looks like scalar multiplication all at once. But any questions first, folks, with dealing with finding the length of a vector? Okay, well, let's try this all over again. Here, we have a linear combination, but think of this as an order of operations problem as well. Even though these are new looking operators for a different kind of space, we're working in R2 because of the two components on all those vectors. The operations that we expect to work through order of operations do in fact happen over here as well. We need to do the scalar products first, in other words, the scalar multiplications, before we do any of the vector additions. So first for the 2a, the scalar product is written down in a pretty complicated way, but it's always saying go down to A and double each one of the entries of this. So 2a would turn to 2a. Then for minus b, I think of that as a scalar multiplication as well. That's -1 as a scalar multiplying b. So let's rewrite this as, go back to the vector b up here, multiply through by -1, and you have a 3, 5. Really, I like to eliminate that -1 so I don't have too many double negations going on. So it's just a way to be more stable in adding these together. The last one is 4 times c. So we come over here, multiply all entries by 4, and now we have a 0, 4. Then finally, the vector addition operation way up here is just telling us when we take x plus y, or maybe it's x plus y plus z, we just add up all the components in the corresponding order. So we'll have to add up the first components, add up all the second components, and then we'll be done. So our first component is 2 plus 3, so just a 5. Second components is 2 plus 8 plus 4, so that looks like a 17. And at that stage, we've done it, folks. The linear combination of twice the vector A minus the vector B plus the vector 4c gives us the new vector 517. Well, any questions at all, folks, getting that result? Okay, looks like I have one more on this set, so let's keep on going. Kind of relaxing mathematics in a way. There's nothing too much major we're doing here. We just have to be fluent to what the structures look like, how to do the arithmetic on them, and getting through the homework will get you in a great spot. This one is a little bit more built up. We're now using the dot product operator. The way this one is defined is by x dot y is the summation of the corresponding entries of x and the corresponding entries of y multiplied together. And I guess I said the summation part, so I can't say add them all up. That'd be redundant. But that's the idea with the dot product. Here, we want to take the length, the dot product with a by c, rescaling b. So there's actually a lot of operations going on here. Let's start off with just a dot c. Let's break it down to this part. So a dot product with c means we go to the entries in A, corresponding entries in C, multiply them, and sum them as we go. So first one will be 1 times 0, plus, next will be 4 times 1. So we get a value of 4 altogether from A dot C. Now our larger problem can be rewritten as the length of A dot C rescaling B is now equal to the length of 4 times B. Here, it's now a sort of choose your own adventure kind of problem. Some people would rescale B. We would get -12, -20, find the length of that vector. But there's actually a different way you can go at this. That scalar right there at 4 could be rewritten as this way. Take the absolute value 4, multiply by the length of the vector B, and that's a valid formula you can apply anytime you're doing this kind of work right here. So the absolute values are just in case my scalar 4 was negative, so they can be dropped right away. And we've already done the length of B. We found out that's just 34. So this comes out as a 4 by, I said 34, it's actually the square root of 34. And that would be our answer if we did it in this kind of clever way, where we didn't actually find the length, or excuse me, the vector 4 times B. We just multiplied the length of B by 4, which makes sense. If we rescale it by 4, we're just quadrupling its length. Well, any questions at all, folks, doing it that way? Okay, I'd say this is definitely, again, a good shortcut to take just for time-saving steps and that kind of stuff. And especially if you wanted your answer reduced as much as feasibly possible. I don't have instructions that say that. I'm not that picky, but if you really wanted a reduced answer, this is the best way to go. Well, for what we're going to get into next, we'll look into some matters dealing with matrices. But think of, for example, vectors. That's just a finite set or a list. When you go into a matrix, you're taking multiple things like this. These could be thought of as the rows of a matrix or the columns of the matrix. In other words, you can rethink about a matrix by saying it's a set of sets, not too different from a power set, or you can think of it as a list of lists, in other words. So that will be our next type of objects to get into on these notes. Looks like we're about done with these notes as well. I think the timing on these are pretty tricky. Some of these sections are longer than I thought. Some of them go a little bit faster, but we'll get it figured out as we work through the text. Any last questions at all so far, folks, before we go to the next? Okay, these are then the last concepts on these notes. Lots of notation and words to get through on this, but now we're looking at n by m matrices. We'll think of the first entry here, n, being the number of rows in our matrix. The m is going to be the number of columns in the matrix. And you know, already that's kind of vague when you say it that way. Let's add just a little bit more structure here by just putting down a really fast example. So here's a matrix, let's call it A. Usually these are indicated by capital letters at the start of the alphabet. I want this A to be of size, let's say A is of size, let's go with 3 by 2. And just put down a random example. Well, first, 3 right here refers to the number of rows. And when we say that, we mean going this way. The 2 right here is referring to the number of columns. And by columns, we mean going this way. Honestly, the first time I had to deal with matrices, this was my biggest struggle. Mixing columns and rows is really, really bad because there's a lot of information, definitions, and theorems that refer to the row specifically or the column specifically. Having that fog in your head makes anything you're doing with matrices really, really rough. So this is a good point to just be really careful. We're going rows this way, columns this way. And sometimes when we're being even more careful, we write down this. A is of size 3 by 2, but we can put a superscript or something down below by saying 2 by 3, just to be specific about the size of that matrix. That actually matters when we're adding matrices or multiplying matrices even more, just by simply writing down the dimension. So here's that example as we mentioned. I'll go column-wise. In column 1, I have 1, 2, 3. In column 2, we'll go 4, 5, 6. So not a lot of creativity, but we've got it, folks. That's our First matrix of the course. Any questions at all, folks, about writing down matrices? Okay, and just for another bit of extra notation to put in here, notice that you can think of 1, 2, 3 as being just a vector itself. Maybe you would call that a column vector to be specific. You could think of 2, 5 as being a vector itself. You might call it a row vector being specific. So the matrix A is either made out of column vectors, of which there are 2, or row vectors, of which there are 3. And this notation is useful just on its own. If I write down, say, the column 1, 2, 3, we would say that that is in R3, because this vector has 3 components altogether. But the matrix A that we just wrote down, we have this following. A is in, let's use our special symbol, element of, or is in, R 3 by 2. So now we build up the notation on R right here to write out in this way when M is inside this larger space. So this is the set of, well, there's lots of ways to say it. It's a set of all matrices that contain either 2 column vectors coming out of R3, put down in a definite order, or it's the set of all matrices consisting of row vectors from R2, put down in a definite order. Row 1 has to be here, for example. So that's our next set that we're trying to get a good handle on. M by N as a space. But any questions so far, folks, looking at these vectors or their notations? Okay, other interesting things here are the so-called identity matrix. If we write down our identity matrix, here's our author's as fancy as possible way of writing it down. I is our way of referring to the identity matrix. But notice where it comes out of. It says N by N, and that's actually pretty restricted. N by M allowed us to have a different amount of rows and a different amount of columns. But when you say N by M, we're referring to squared matrices only. So an identity matrix cannot have more rows and columns or vice versa. And that's what the Rn by N is saying already. These are really very subtle when you read through right here. The author is saying a tremendous amount of information just with that statement. So when people say you have to read through the lines when you read a mathematical definition, that's what's being meant right here. Then he specifies it in this way. The entries of the matrix, we specify them as Ij. I would be the ith row, j is the jth column. If I equals j, it's going to be a 1. Otherwise, it'll be a 0 when I is not equal to j. So we ought to write down a matrix just like that for the practice. Let's say I is in R4 by 4. So a 4 by 4 identity matrix. This would imply I would look like this. I need 4 rows, 4 columns. So your matrix should look pretty square. The ij right here, again, is referring to a row and a column. Right where the red dot is, I'm in row 1, column 1. So we would have I equals 1, j equals 1, and it tells us the entry here should be a 1. Now let's go column-wise. Down this way, I'm in row 2, column 1. Let me add another pen here just to show this information. This is the 1, 1 entry. Here, the next entry we're about to put down, this is row 2, but still column 1 entry. So this would be 2, 1. That's important because it's being referred to right here for the entries. But when we're in 2, 1, I takes on the value of 2, j takes on the value of 1. They're not equal, so we put down a 0 here. So there's the 0. And certainly, as we go down the list, they're all unequal, so we'll go 0, 0. This is a 3, 1 entry, and that is the 4, 1 entry. As we come down here, we're at the, let's see. Let's leave this one to the class. What entry would you give this with subscripts? Is this 1, 2, 2, 1 otherwise? Good call. From the class, this is the 1-2 entry that goes right here. Because we're in row 1, but now we moved to the right over to column 2. So this is 1-2 entry, but the indices are different here. So we go and use the 0 on this one. Finally, we go down to this entry. I'm going to start stop writing down the purple stuff because I'm running out of space. But that would be the 2-2 entry. The indices match up right here. So in this location, we would put down a 1. And in fact, the name of this game is 1 just emerges on the main diagonal. There's zeros elsewhere. So we'll get 0, 0, 0, 0. Here's the next main diagonal entry going this way. And that would be the 3-3 entry. We're in row 3, column 3. Then 0, 0, 0, 0. But here, that's the 4-4 entry. So we put down a 1 here as well. So that's the way to write down the identity matrix. And this approach of writing it down this way, it's great. It's as fast as possible. That's a compact statement. But the downside is if you write down your definition this way, you also have to unpack it. So that's what we're doing over here, just to try to understand it. So usually we just write down identity matrices just right away. But working out slowly here was just a way to try to understand what are those indices saying about the entries, because that's kind of tricky all on its own. Again, you have to have a strong handling on what are the rows, what are the columns. And maybe last statement here, just as a reminder, this is the A. It's in row 2, column 2 entry. So we say that entry is 5, much like how we write ij down here. Well, we have identity matrices, general matrices. Only requirement on the identity ones is that they're square. And going down below, we have what seems to be a really kind of highly abstract definition for matrix addition, scalar multiplication. But actually, what we're doing here is algebraically totally identical to what we did when they were vectors. So let's take a look at the definitions. The first thing we're looking at here is, given a matrix M, a scalar, or just call it a real number in R, we're interested in the product, we'll call it a scalar product, A times M. It's a new matrix N. The entries are Nij, but they're formed by just taking whatever A is multiplied by Mij. So as an example, we took 5 times A. That would just mean go to every entry multiplied by 5. So this entry would be 5 times A22, is what's being said right over here, as abstractly as possible. But again, think of what we did with the vectors. We're just taking the corresponding entries from the right row and column and strictly just adding them, multiply them together. We're doing an addition. The next definition just says, add those corresponding entries. So our author is in a habit of writing down these definitions very abstractly, as densely as possible. But that's because part of the textbook is to get used to these symbols, like element of, to get used to dealing with indices like 1 through n, and to get used to functions being defined in case-by-case basis like what's up here. So it has the side effect of being the fastest way you can write things down by these notations, or close to it. But it has a side effect. We have to practice unpacking these definitions like we mentioned. Any questions at all, folks, on looking through either one of these concepts before we tried the examples?
Did you mean to write 3 by 2 under the A array
Oh, let me see here.
or matrix? My fault.
No, that should have been a 3 by 2 right here. Thanks for spotting that. I should have said 3 rows. Not too sure what I was thinking when I was writing that down. 3 rows, 2 columns. I even had it color coded. That didn't help me at all, apparently. Thanks for spotting that. Does that look better with the correction there?
Yeah.
Awesome. Thanks again for spotting that, Corbin. Other questions so far? Okay, always good to catch those little weird mistakes because we can get them in the notes, but it's on the YouTube video forever. Those are not so easily fixed, so I appreciate it. But let's try this all out again on the examples down below. So we have 3 random looking matrices. The object of this is to evaluate each of the following, but we also want to watch out for the undefines. In our work and the homework, we'll have to say when things are undefined and also explain why. But these explanations, they can be very, very brief. So if all you do is what we do in our notes for the explanations, I'll be happy with that as well. Just to be specific, I said that I came from the R3x3, and it's also the identity matrix as well. So first thing we're going to do is a scalar multiplication, -5 times I. If I is the matrix that goes like this, but it's size 3x3, so it's cut a little short, all we're doing is multiplying all entries by 5. It looks like we're just getting 5 along the main diagonal, or -5 rather, forgot the sign on there. To really write it out, here's how it would look. It's -5 by going column-wise, 1, 0, 0, 0, 1, 0, 0, 0, 1. Because we only have ones on the main diagonal highlighted in yellow, that's how we know it really is the identity matrix. The moment we change anything, no matter by how small, if you put, say, 0.1 here, it's no longer the identity matrix. But then once it's written out, again, we're multiplying every single entry by -5. We like the zeros because that makes it fast. We just get -5, 0, 0, 0, -5, 0, and 0, 0, -5. And we did it, folks. That's our whole operation on this one. Next one is a linear combination, almost the same kind of thing that we did on the prior section for vectors. And then we'll try another linear combination, it looks like. Any questions first, folks, with our part A? Okay, well, if it's A plus B plus 5i, there's no harm in just writing down this. Start with your matrix, put down the answer. You would know if you're taking A plus B, you're taking 0 plus 1 minus 5, dropping it down here. And if that works for you, that's totally fine for me as well. But for me, I find that for some reason or another, is actually pretty tough on me. There's a lots of arrows that your eyes has to jump through, hoops to go through. For me, I'm way, way more accurate if I just write down the matrix. So I'm going to drop in A here, 0, 1, 3, 3, 5, -2, -4, 0, 7, plus the matrix B. I'm just going to write it down so it's available, 1, 0, -2, 5, 4, 3, 11, -3, 0, plus -5 times the identity matrix goes -5, 0, 0, 0, -5, 0, 0, 0, -5. Only downside with this strategy is your hand can get tired. That's a lot of copying. But now as you run through this, your eyes are just going left to right. Your accuracy is almost guaranteed to be way, way up. You're probably going to be way faster. So the time lost right here, you could actually reclaim it doing it this way. All depends on you. But for the first entry, it'll be 0 plus 1 minus 5 for a -4. I'm going to go downward, so build out the first column. So now I'm at the 2, 1 entries. 1 plus 0 for a 1. Then 3 minus 2 plus 0. Notice this matrix only comes in once the main diagonal is in use. So I'm just going to think of this as 3 minus 2 for the 1. Up here, we have 3 plus 5 for an 8. This one's on the main diagonal, so we'll use all 3 matrices. 3 plus 4 for a 9, minus 5 for back to 4. Let me know if a number goes sideways. -2 plus 3 for a 1. And this is our final column. Will be -4 plus 11 for a +7. 0 minus 3, so we're at -3. This one's on the main diagonal, so all 3 matrices. 7 plus 0 minus 5. And we get a value of 2 on that one. So this one's a linear combination. We get that as a whole result.
The bottom line on bottom row of matrix A 3 to 7, not the -7.
Oh, that was my bad. That's my error of copying things in a weird way. Thanks for spotting that one. That should have been a +2. So it's 2 plus 3 for a 5 altogether. So that affects, yeah. So here to here. Thanks for spotting that number there. I don't see any weird miscopying as well after that one. Really good eye on that one. Thanks for spotting it. Okay, I guess this strategy only works if you very meticulously copy the matrices down and don't make any errors there. Let's try out the new one, 3C plus 5B. Well, before we get too far, if it says 3 times C, we'd be taking 3 times 130, 111, plus 5 times the matrix B is of a different size, 1, 0, -2, 5, 4, 3, 11, -3, 0. I'll leave this one up to the class. It probably looks weird to your eye. What would you say for this one? That's correct. In class, the statement was, can we not add matrices of different sizes? And that's absolutely true. The moment we see different size matrices that we're trying to add, this is automatically undefined. And so we should say so right here. Undefined. So we said it's undefined. That's this portion here. We have to explain why, but you can be very brief on this. I'm not expecting too much. All I'm really expecting you to say is the matrices being plural of matrix, the matrices are of different sizes. The first matrix is non-square of size 3 rows, 2 columns. Second matrix is square of size 3 by 3. But there's no way we could add these, no matter if we change the order or anything like that. So that's our first undefined for this section notes. Well, we did, folks. There's not too much to say about dealing with these structures until we get into matrix multiplication, and suddenly that does get pretty interesting. We'll take a look at that next. Any last questions or comments whatsoever for example 3? Okay, well, here's our next set of operations, matrix multiplication. This is where the notes are also going to end, as well as the homework exercises. And I'm at that weird part of class where I have a little bit less than 7 minutes. But let's give this a try. We might give one of these operations a go if we have time. So for matrix multiplication, we have it indicated this way, A times B, just an ordinary product, like 5 by 3. But there's one thing we have to pay really close attention. Saying A is an element of R n by m is just a way of saying, well, it can be of any size. It doesn't have to be square. But that m right there turns out to be extremely important. The matrix B, it also can be square, not square, that's okay. But there's suddenly a firm requirement right here. If this has m columns, B has to have m rows, and that's a firm requirement. Or just like the last problem we did here, where there's a dimension mismatch, in matrix multiplication, this is the mismatch. This is what makes matrix multiplication undefined. So let's say this right here. We're looking at the number of columns in the matrix A, number of rows in the matrix B, and we can say if these are not equal, A times B is undefined. So we require equality right there. One way to say that is when you take a matrix, say A times a matrix times B, or looks like C is the first one, if we can form that product, it turns out to be a dot product. We take, say, this row, dot product with that column, and that's one reason it would be defined. But for A times C, let's take a look at these. We can't take the dot product of, say, well, hang on, let's take a look at that matrix A. The matrix A on this one is of size 3 by 3. It's multiplying the matrix C, which is of size 3 by 2. That tells us this matrix multiplication is defined. even though the matrices have different sizes, we can multiply these two together, is what this is saying. Then finally, for the definition of matrix multiplication, as our author writes it, we get a new matrix M of size n by p. And the n and the p here are very specific now at this stage. The n came from here, the number of rows. The p comes from here, the number of columns. So A times C is undefined and is of size. Grabbing the outer dimensions, the 3 and the 2 here, we'll say it's of size 3 by 2. So that will be a matrix product that we can evaluate. There's some undefineds on here, so we'll get to those when we get to them. Our author's definition for this is, again, pretty complicated. He's got some formula with products involved, but notice the thing that's fixed here. When the I is fixed, when it's equal to 1, and K moves, that means you're staying in the kth column, but moving down the ith row. Here, we'd be moving down the kth row and down the jth column as well. So the definition here is really pretty rough, but really it's all a matter of doing dot products. So we'll see how to get that definition working. I mentioned here for the example, turns out matrix multiplication is all of the fanfare in mathematics these days as it relates to generative AI, large language models. So if you're really curious on what that looks visually, take a look at this video here. These are totally optional, but this one was done by a gentleman named 3 Blue 1 Brown, if I recall correctly. He uses some extremely fancy graphics to illustrate how the mathematics is working on all this kind of content. So if you want a good application of matrix multiplication, this is where it's at currently. And it turns out, it looks like they found a new numerical way to implement matrix multiplication, which is bizarre and kind of exciting as well for that field. But I think this is a good stopping point for us. We're not going to rush through A times C when it's a pretty complicated product, and we're just about out of time. So this will be our first problem when we come back on Thursday's class. But any last questions or comments whatsoever, folks, before we call it a night? Okay, well, have a great night, folks. Thanks for the contribution and participations on the notes, especially for those weird typos and miscopied. I really appreciate it. We'll be back to these notes when we come back on Thursday, but drive safe and I'll see you all in that next class.
Thank you.
Yep, absolutely. I said drive safe when most of the classes in Zoom, but it just felt like the right thing to say.
I have a question for the corrections you did on my assignment 2.2.
Sure, absolutely.
So you marked, let's see, the 2.58 as wrong, but I'm not sure.
Let me
I
save
think-
this up, take a look at it with you.
Okay.
Or can you tell me how that problem goes? That might be a little bit faster.
So it's -42 mod 17, and you corrected it to be +9.
Yeah, that one's pretty weird if I recall. What makes it weird is the negative value that you're dealing with in the modular arithmetic. So best way to attack this thing is to go at it by formula. We will go -42 minus 17, take the floor of -42/17. So this right here is the formula that we were using on the prior problems, but honestly, because if this is positive, we think of modular arithmetic as the remainder out after division, we may not have actually used that formula directly. But when we use it here, here's how it goes. -42 minus 17. Actually, do need a calculator for this part. Let me pull it up quickly. Usually try to open this up, but this is one of those days I forgot before class started. So I just need a -42/17. We've got about -2.47. So this is the floor of -2.47. At this stage, it turns into -42 minus 17. This floor here becomes a -3. And that's where the +9 comes out from this right here. Let me double check that arithmetic. It looks kind of fishy to me. Negative 42 minus 17 by negative 3. Yeah, that's how we get the 9. And this 9 is just telling us where the closest multiple of 17 is to 42 on the number line, whenever this is now a negative quantity.
Interesting. Because I
Yeah, it's
double
pretty-
checked like once I saw the correction in code, like I just did the thing in code and it gave me the same answer I did.
Strange. Yeah.
Really?
By our author's definition right here, we were expecting a 9. But you know what? Let me see just how good Desmos can do. This is not the same platform, certainly, that you're using, but negative 42 mod 17. Oh, it doesn't look like it's happy with that.
You could try a
Another
percent. Maybe it doesn't use the mod keyword.
Negative 42 mod this way. Oh, as soon as I hit percent, it typed in the of. That's not a good sign. Negative 42%. And it deletes it the moment I try to get the of out of there. Looks like it doesn't accept that kind of syntax, but let me try another one. Wolfram alpha. This one's usually pretty good for a wider selection of functions. And let's go negative 42 mod 9. They say a result of 3. Weird.
I think
So
it's
what's that-
supposed to be mod 17 instead of mod 9.
Oh, yeah, 9 was the answer. Mod 17, let's see what they got on that. Yeah, they're going with the 9 on this one. And I think this is what they're trying to express here with the number line. Maybe? No. Integers congruent to 9 mod 17. That doesn't really help us. Well, our author's explanation on why 9 was more go like this. So here's negative 42. And if we start looking at multiples, let's say, oops, negative 17 by 2, we're at negative 34. And we're doing mod 17. We got a 9. Starting to get kind of foggy on the interpretation on this one. So
It's just weird to me how a negative number divided by a positive number can have a positive remainder. It doesn't really make
right,
sense to me.
as soon as we put the negative number in there, we lost that analogy of the remainder after division. Oh, I think I've got the answer or a better thought here. Yeah.
Computed negative as a, you're most likely working out of the spot in memory. And if you pass 0, there's like nothing there.
It would
But
sign and unsigned.
Gotcha.
mathematically, like, if mathematically the application of modulus demands a plus.
Gotcha. So there's applications to that. I see. I think that's a great analogy. Thanks for mentioning that. Another way to think about this is when you think of 17, the negative 51 right here was, hang on, let me get that. It was the third multiple of negative 17. The negative 34 is the second multiple of negative 17. The distance from here to here compared to the distance from here to here, let's work those out. Whoa, that's the console. So I have negative 51 minus negative 42. And I have negative 42 minus negative 34. So I have a distance of 8 and a distance of 9 going here and here. And this is our author's explanation for the result of the formula. When there's a negative number here and you do modular arithmetic, yeah, it's really hard to say, what does that mean in terms of remainder after long divisions? But what you get as an answer is the longest distance between the nearest multiple of the thing you're doing modular arithmetic by. So the largest distance was 9 going this way versus 8 going that way. Just double checking my numbers typed in. But does it help out to see it that different way?
Yeah, I think the reason why I got it wrong is just I have I have coder brain, not math brain. So it kind of just, I looked
Gotcha.
at it in a different way instead of following the formula. So that makes more sense.
Gotcha. For me, what happened when I was doing this homework set myself was I saw the negative there. I thought, I have no clue what this means now. So I grabbed the formula, got a result, and I didn't really believe it. And then at that point, I just read what the author had to say about it. He was able to convince me, so I just moved on from that point. But thanks for bringing that to our attention. It's a pretty weird operation for sure with that negative. Well, folks, I got to move over to the next class, but thanks for asking about that one.
Yep. Thank you. Have a good day.
You too. Take care.